Hello, my name is Zachary Siegel, and today I'm excited to talk about CoreBench, which is the Computational Reproducibility Agent Benchmark. So to start, I'd like to talk a little bit about what computational reproducibility is. It's the ability to reproduce the results of a scientific study using the data and code provided by the authors. So you might hope and expect that most scientific papers online are computationally reproducible, because if you're given the exact code and the data, of course you should expect to get the same results of what the paper says. However, there are many challenges in practice associated with computational reproducibility. In some cases, authors don't upload the code online, but even when the code is uploaded, there are often issues installing the right versions of the libraries and dependencies. The code might have bugs or might be out of date and not the same version that the authors used to run the experiment. Or there might be, for example, variants in the hardware used to run the experiments, which could account for differences in results. In practice, it turns out that there is a widespread reproducibility crisis across many different fields, meaning that papers across multiple fields are not computationally reproducible. And the motivation for our benchmark is to see if AI agents can verify computational reproducibility in published scientific research, because this would make it a lot more efficient to verify whether existing papers are computationally reproducible and could help begin to address the problems that we face. Just to drive the point home, we conducted a survey over multiple different papers that analyzed computational reproducibility across different fields, and you can see that across many, many different areas, there are reproducibility problems. Just take NLP. Of the 549 papers surveyed, 472 of them were identified as having issues with computational reproducibility. So this is an issue that impacts all of science, not just certain fields. So to give a brief overview of our benchmark, we have 270 tasks, which we draw from 90 different published research papers. We find our research papers from a website called codeocean.com, which has papers that are verified to be computationally reproducible. That way we can attribute any failures to reproduce a paper to the agent and not because the paper is inherently irreproducible. We draw papers from the fields of computer science, social sciences, and medicine, and agents are evaluated on their ability to correctly answer questions which we construct about the expected code output of repositories associated with the scientific papers. So for example, one question might be, what is the train accuracy at the end of training of the neural network? And the agent would be expected to reproduce the paper given the code and obtain the same train accuracy as what the authors report in their own paper. And it follows, of course, that high-performing agents on this benchmark should have real-world utility, because it means that they could be used to verify the computational reproducibility of papers in the wild, not just on our benchmark. So here's an example of what the pipeline looks like. The agent is given a task prompt, such as run a particular script. The agent is also given the set of task questions that we construct that we want it to answer. So in this case, one is report the y-axis of a particular label on the graph. And the agent is as well given the code repository, which allows it to reproduce the paper. The agent runs and then is expected to report answers to all of the task questions, which we then evaluate, and a task is considered correct if the agent has successfully answered all of the task questions. We provide tasks at 3 different levels of difficulty, and this is what allows us to come up with 270 tasks from only 90 papers. The easy tasks are where the agent is already provided with the outputs of the code, so the agent doesn't need to run any code, and all it has to do is read through the results to answer the task questions. This isn't entirely trivial because the results could be in paper manuscripts or plots or across many different files, so this retrieval process does take some time and effort. For the medium tasks, the agent is provided with a Docker command which it can execute to reproduce the code. Other than that, it's pretty similar to the easy task level, and this is mainly evaluating the agent's ability to use the terminal to execute commands. And finally, we have the hard tasks. These are where the agent is only provided with the code of the paper, and it must on its own install all of the libraries and dependencies, as well as figure out the correct command to run the code and read through all of the results to answer the task questions. This hard level of difficulty is most akin to what reproducing a paper in the wild would be like. So we evaluate 2 different agents on our benchmark. The first is called AutoGPT, which is an open source agent that uses large language models to take actions in its environment. It's given abilities such as the ability to execute arbitrary terminal commands, to write and read from files, and it can also summarize its own past actions, which it then uses to determine what future actions should be taken. On top of that, we create an agent called Core Agent, which is based on AutoGPT, but it is given prompts with specific guidance for CoreBench in order to improve performance. We also give it a vision language model tool, which allows it to analyze the results of plots and figures. And we also only allow the agent to return once it has successfully submitted answers to all of the task questions. This prevents the agent from returning if it forgets to answer the task questions or doesn't answer them in the correct format. So to see the results, you can see that in general, Core Agent with GPT-4o is the highest performing agent. This makes sense because the task-specific modifications allow it to perform better than AutoGPT, and the stronger model, GPT-4o, outperforms GPT-4o Mini. You can also see that the results on the hard tasks are the lowest compared to the medium and easy, which also makes sense because hard requires the agents to do the most amount of steps, including installing all of the dependencies and libraries. The high-level takeaway here is that making minor modifications to AutoGPT, which allowed us to build Core Agent, we're actually able to produce significantly improved results. And we think this shows that often generalist agents themselves don't need to be the highest performing on a benchmark, so long as it is easy to customize it for your particular task. You might be wondering why agents fail or how agents fail on our benchmark, so we did a qualitative analysis of the reasons for agent failures on Core Bench Hard. We found that in the majority of cases, 57% of the time, the agent incorrectly installed the dependencies, which caused it to be unable to proceed further in the benchmark. In cases where the agent did correctly install the dependencies, you can see 20% of the time the agent ran the code incorrectly because it didn't determine what the correct command was to actually produce the intended results. And finally, in the remaining 23% of the time, the agent was able to correctly install the dependencies and run the code, but it had problems actually retrieving the correct output for the task question from all of the code outputs. And this is because, as I mentioned, the code outputs can often be distributed across many different files or in different plots, so this is certainly a non-trivial step. In conclusion, we think Core Bench highlights the potential that agents can use to automate computational reproducibility, but we're still a far ways off. Our highest performing agent still gets under 20% accuracy on the hardest level of tasks on our benchmark. High performing agents can be deployed in the real world to verify if papers are reproducible, but we're not there yet. But we believe this shows the promise of using Core Bench as a way to improve the abilities of agents. That way we have a way to assess their abilities before deploying them in the real world. We also would love to encourage all of you to submit your own agents to our benchmark, and then you can check out how they stack up against our existing agents on the leaderboard, which you can see on the GitHub link below. Of course, if you have any questions or would like to collaborate with us, we're more than happy to talk, and I encourage you to reach out to us or any of the other authors. Thank you very much.